In this example, we're going to be calculating the standard enthalpy change. So that's delta H naught, not meaning it's at standard conditions for the reaction of the combustion of C6H6. And in order to do that, we'll use this equation. And this equation says that the standard heat of reaction is going to be equal to, this symbol means the sum of, so that's capital Greek letter delta. The N stands for the number of moles, meaning the coefficient, and you're going to multiply that by the heat of formation of each of the product, the standard heat of formation of the product. You'll subtract from that the sum of the coefficient times the standard heat of formation for each reactant. You sum those up. You subtract these two, and then that will give you your standard heat of reaction for the combustion of the C6H6. So in order to do this, we need to look up the standard heat of formations, which are listed in tables. If you look at the end of your textbook, there are pages and pages of heats of formation. I have one that's a little simpler to read, though it does still have some information that that is superfluous, because I wanted you to be able to kind of suss out what you will and will not need. If we look at this chart in terms of our reactants, we have C6H6 liquid. So by definition, standard heat of formation is the amount of energy either released or gained when 1 mole of the compound is formed from its elements in its standard state. And it looks like C6H6 is actually endothermic. In order to make it, you have to put a little bit of energy in. And you'll see in the next example the reason why. When we look at the Lewis structure, there's some ring strain for that. And since we just have a 1 as the coefficient, you're not going to need to do anything with that value. Now let's look at the O2 value. It's 0. Well, because the way the element oxygen occurs in its standard state is as O2 gas. So there's no energy change for that one. If we now look to our product side, I'll do these in pink, we have carbon dioxide, and that's carbon dioxide gas. So here I put both carbon monoxide and carbon dioxide, just so you'd have to pick between the two. You want to pick the right one. So carbon dioxide, so we have heat released here when we form 1 mole of it from its elements in its standard state, negative 393.5. However, don't forget you have a coefficient of 6 in front of that. So you'll want to multiply this by 6 when we get to our calculation. And then our last order of business is to deal with our last product, which is the liquid water. Now notice I have water in 2 different states here, so make sure you pick the right one. We want the liquid for this problem. Okay, and then there are 3 moles of the water, so we're going to take this value and we're going to multiply it by 3. So anything that's in yellow, you're going to sum up. Anything that's in pink, you're going to sum up. And then you're going to subtract the yellow from the pink in order to get the overall heat of reaction. I plugged in my numbers to the formula. And when you do the calculation, you should get negative 3,267.4 kilojoules. Notice here that you have kilojoules per mole, but in multiplying through by the coefficients, the mole cancels. So this is kilojoules. It's typically said kilojoules per reaction, so per kind of one time of the reaction going through. Other things to notice here, sig figs are not super important here, but you are doing some addition and subtraction, so you're going to go with the fewest number of decimals, and that's going to be 1 decimal place. Something else you can take away, there's a negative sign here, so that means that apparently this reaction at standard conditions is exothermic. And the last takeaway is that anytime you use heats of formation to figure out the heat of reaction of a specific reaction, you're actually using Hess's law, right? So it would be a very lengthy exercise, but we could actually write out the reactions for the standard heats of formation for each of these compounds. Okay. And then you manipulate those so that in the end it adds up to this reaction. And guess what answer you would get? You would absolutely get this answer. So using heat of formation is actually a use of Hess's law.